All right. Thanks for having me. I realized something. So I'm the last talk of the afternoon. I was trying to think about what to say after we've had a lot of talks with a lot of detail on several concepts and such. So I'm going to try to have a somewhat more aspirational talk about the needs and the opportunities for the future and where we need to go. We've had some great guidance come down the line from the Decadal, which is going to help mold the future of astrophysics in the US here over the next 10 years. But there's a lot of work that needs to be done to figure out the details of the path. And so I hope I end the talk here with, some of the early career folks here looking at the sort of looking at the future and thinking, looking for opportunities of where they can provide some helpful work to build towards these decadal goals. So we've just had several talks on the concept, so I'm not going to go into any of them in detail. I'm not in a position I'm going to promote any of them in detail. So I apologize if I don't talk about your favorite study in detail, and I realize there's some not even on here. I noticed we didn't have we'd heard a little bit about Thea, but I thought there might be a separate talk on it. There's, we've heard some about Jasmine, the guy in the Near-IR mission, Ptolemy, what astrometry is possible with the Roman Space Telescope. We just heard from Alberto a little bit about what could be done with the Thea. But I'm not going to go into any of them in detail. So for the people watching on YouTube, go find the talks for those speakers. So I'm Deputy Program Chief Scientist in the NASA Exoplanet Exploration Program. If you think about NASA, there's NASA, the Science Mission Directorate, Astrophysics, and under Astrophysics, there's Physics of the Cosmos, Cosmic Origins, and the Exoplanet Exploration Program. And so some of the science and technology work related to exoplanets is in our program. Part of our charter is discover planets on other stars, characterize their properties, identify candidates that could harbor life. We currently don't have any flight missions. Kepler was part of our program. Roman early on as W1st was part of our program, but we currently don't have any flight missions in the program. Currently, we have a lot of technology development related to exoplanets and some science support. If you look at, this is just our slide. I apologize to the people that attend ExoPAC meetings and such. They've probably seen this slide 1,000 times. But EXEP provides support for some of the mission concept studies, ground-based support, time on some of the telescopes for science of strategic value to NASA, especially related to exoplanets. We do a lot of technology development, things, chronograph technology, starship technology, we're now doing EPRV technology. NextEye, which runs the second workshops, is part of EXEP. And you've probably seen some of our posters and such from our communications team in EXEP. There's the Roasted Planet, which was last year's poster. So starting off aspirational, I always have to take myself back to being an observational astronomer. This is one of my favorite sites in the world, Cerro Tololo. You can go up there in the middle of the night, on a night where there's no moon, look up, look at the galactic bulge. You can see your shadow from starlight when there's no lights from any of the cities or anything. You're actually illuminated by the light of the billions and billions of stars in the galaxy. It reminds you of why you're an astronomer. And we now know the Milky Way has roughly 50 billion solar masses of stellar stuff of stars. Your typical star in a solar neighborhood is about 0.4 solar masses. We're talking about something like 125 billion stars in the galaxy. The Kepler survey, which ran early last decade, gave us the statistical results of planet frequency for close-in planets. It stared at a region in Cygnus and Lyra region. And if you look at the breakdown by stars, we sort of have lower limits just for the counts of planets, the frequency of planets within a couple 100-day orbits. And there's something on the order of a few planets per star, just on average for the stellar types. Something like 72% of the stars in a solar neighborhood are M dwarfs. So if you figured out M dwarfs, you figured out most of the stars in the galaxy. But as we'll see later on, for the direct imaging, we're mainly worried about the solar type stars, the FGK stars. But what's this work out to? We've got a lot of exoplanet exploration ahead of us. We're talking about a galaxy with over 400 billion planets. And this is just based off of the statistics for the close-in planets. We're probably talking about trillions of planets to discover. And we're obviously interested in ones that might be abodes for life. The frequency of the small rocky planets in the so-called habitable zone, depending on how you define it, is something like a quarter. And for M dwarfs, it's something like a third, based off of the latest analyses based off the Kepler mission. These numbers there's an asterisk next to the sun-like star one. That's fairly controversial. It's probably somewhere between about 0.05 and 0.5. There's some spread among the groups that are quoting values for it. The problem is Kepler just touched on the Earth-sized planets in the habitable zone, and this didn't build up a lot of statistics there, so there's a bit of extrapolation. Gaia has helped significantly with the interpretation of the stellar properties, so we have the constraints on the planets much better, but there still was just too few planets found. But ballpark, we're talking about something like 30 billion planets in the habitable zone, rocky size, something between about 0.5 and 1.5 times the Earth's radius that are going to be places to search for life. Although a lot of these are going to be very distant, we're really interested in the ones that are very nearby. Now here's the nearest star, our sun, and its planetary system. When I was very early career, high school, this image came out from Voyager. This is about 30 years old. This is the family portrait from Voyager 1. After Voyager 1 passed Saturn, it flew over Titan and kind of went off at an angle out of the solar system, and it turned back about 8 or 9 years later, and it took the sequence of images of the planets. This was our family portrait of the solar system from outside the solar system. And all the planets were these small dots. And of course, there was this pale blue dot this quite famous image. This was became the source of the title for Carl Sagan's book in the mid-90s, The Pale Blue Dot. And so, we wondered what would it look like to image planets around nearby stars. When this image was taken, there were no confirmed planets. There was only a couple candidates. The pulsar planets wouldn't be discovered until around 91 or 92. There was a couple controversial cases between 1990, but we were right at the cusp of the explosion of extrasolar planet discoveries over the last 30 years. As the other speakers mentioned, we're all bound by law to show the movie from the images taken from several observatories here. I think they're mostly from Keck. The HR 8799 4-planet system here on the left. Unfortunately, the title's off the bottom, but this is from Jason Wong. This is from several years, about half a decade of images of the HR 8799 system. This is a 30 million-year-old system with 4 giant planets between about 5 and 10 Jupiter masses. The one on the right is a little bit more near and dear to my heart. This is a star system, a young star we actually found in a spectroscopic survey about 10 years ago. This Tycho 8998 star, and it turned out a few years ago to be a multi-planet system. So this is from Alex Bond's thesis. He was a student at University of Leiden. This is the first imaged multi-planet system around a sun-like star. I will add a little bonus here for the HR 8799 story. So I was giving a von Karman lecture at JPL 5 years ago and wondering, hasn't anybody produced a movie of the H8799 planets? So I posted this in the exoplanet imaging group on Facebook. You may have heard of Facebook. Anyway, I just said, has anybody made an animation of the 8799 system? So there was a lot of discussion on this. And Jason Wong's like, oh yeah, I can go make one of those. He's like, I just need the images. So Bruce McIntosh and Christian Arroy and Thane Curry and a few others pitched in. And within a few days, Jason Wong emailed and was like, oh, here's a movie of the 8799 system. And within 2 or 3 weeks, it was the astronomy picture of the day, and it was everywhere. But that actually came out of trying to find a nice animation for a talk. So thank you, Jason Wong. I think Aki showed this in her talk. This is the sequence of the Decadal Surveys going back 50 years, going back to 1970s when they first recommended what would become the Hubble Space Telescope. And we've had an interesting run here on the way to look for, let's go look for extrasolar pale blue dots. In 2010, there was some missions before that. There was the TPF concept, SIM also, and they were canceled. But the 2010 Decadal basically said, we're really interested in imaging planets around nearby stars. We're just not there yet to be able to select it. We need to find out more about the frequency of planets around nearby stars. We need to find out more about the dust, how much of a background exozodiacal dust is going to be. And really, there's not a lot of technology development that needs to be done. So go off and do the technology development, go measure these quantities, and then get back to us in 2020. That was basically what the 2010 Decadal said about imaging planets. The 2021, the Decadal that just came out, this is just fantastic. If you're interested in exoplanets and the search for life, it was just wonderful to see the exoplanet community really come together the last few years. My impression was the community was more fragmented about 10 years ago. The last few years, it was much more of a sense that we needed to act war with a single voice on what was most important for studying planets and the search for life. And I think that really shone through. And this is just a fantastic Decadal for telling NASA, telling Congress, telling the taxpayers, telling scientists, early career folks, a really compelling vision going forward on studying planets and studying their properties and searching for life. And so, we now have a path to go find these. Aki showed this in her talk. This is a LUVOIR. This is actually a LUVOIR A. So this is actually for the 15 meter. I have to say that's a bit of a cheat. What we're really going to have is probably something like a 6 meter. Exactly. So this is supposed to be a 12 parsecs. Just bump it up, I think, to a few parsecs. So for a 6 meter. What's that? So what did the Decadal say? It recommended a future great observatories program, an IR optical UV telescope. Some call it LUVEX. Most people don't like LUVEX. Most reasonable people call it IRUV these days. Okay, that's what I was. Sorry, when the NASA astrophysics director started calling it IRUV, we all start calling it IRUV. So, for lack of a better name, someday it'll get a better name, but nobody calls it LUVEX anymore. So, and so it recommended, the next few decades, developing the next fleet of these flagships, one for the far infrared, studying the very cold universe, interstellar medium, galaxies, and also for the high resolution X-ray observatory. But the IRUV would be sort of, a Hubble, but much larger 6 meter class telescope, but with the ability to suppress the starlight sufficiently to detect and spectrally characterize planets. So there's this wonderful passage, this recommendation in the Decadal. After a successful mission technology maturation program, NASA should embark on a mission to realize embark on a program to realize a mission to search for biosignatures from a robust number, about 25 habitable zone planets, and to be a transformational facility for general astrophysics. If mission technology maturation is successful, is determined by an independent review. Implementation should start in the latter part of this decade. Okay. So it's not just an exoplanet mission. It's got to be transformative for astrophysics. So what is astrophysics going to look like in 20 years in the era of ELTs and of the post JWST world? So we need to think about what a transformative UV-IR telescope is going to look like for the rest of astrophysics, studying stars, brown dwarfs, galaxies, etc. But we also want to build a machine that's going to be able to detect at least on the order of 24 small planets around the habitable zones of nearby sun-like stars. So there was the two mission studies. There was LUVOIR A, LUVOIR B. This is just LUVOIR B, 8 meter concept, off-axis telescope, just a coronagraph, no starshade. HabEx was a smaller model, 4 meter monolith telescope with a coronagraph, but also with a starshade. So of course the Decadal picked something sort of in between. And so, in the near future here, we need to start exploring trades on different options for the architecture of what that's going to look like. Now, before the Decadal came out, in 2017, Congress asked the national academies to get the community together and write a couple of reports. One was on exoplanets, characterizing exoplanets, and the other one was on astrobiology. And the exoplanet one, it was perfectly timed because the results were going to come out a year or two before the Decadal. The Astro 2020 Decadal was looking for input. And so this was a real opportunity for the exoplanet community to come together and come up with a vision of what was the exciting science and which options that they were most excited by. And so one of the things they pointed out, not only did they promote the idea of imaging, searching for Earth-like planets on nearby stars, spectrally characterizing them. But they had a big emphasis on the mass. And really, I like this passage here. Mass is the most fundamental property of a planet. Knowledge of a planet's mass, along with knowledge of its radius, is essential to understand its bulk composition and to interpret spectroscopic features in its atmosphere. If scientists seek to study Earth-like planets orbiting sun-like stars, they need to push mass measurements to the sensitivity required of such worlds. So we kind of know what we're aiming for in terms of how accurately we want to measure masses and down to what mass. Mass impacts a lot of the features of planets. You saw this one before. This is just the planets are hard plot from Vicki Meadows and Rory Barnes at University of Washington. This is a great plot in their 2018 review. And several of these on the planet side, all these characteristics are stellar effects, planetary systems, planetary properties. A lot of these planetary properties depend on mass, right? You're studying the interior. You need to know how much stuff is there to model in the planetary interior. The atmosphere is going to, you need to know the surface gravity, the planet mass, and the radius. And so a lot of these parameters depend on the mass, and also the planetary system, putting the system in context. Are there giant planets in the system? What's the eccentricity of the orbit, et cetera? You need to know masses and orbits for those. Now, one of the problems we run into, this is from Li Zhang from a few years back. One of the outcomes of the Kepler mission is that the small planets are a complete zoo of objects between very rocky planets and things like Neptune and things intermediate that we're still trying to get details on. Are some of these water worlds, or some of these rocks with hydrogen helium atmospheres but not much ice? Some of the planets seem to evolve between types. Some of the sub-Neptunes very close in may evolve into super Earths. And again, this zoo of things going on is for very, very close in planets. Once we get out to 1AU, we may not see as well pronounced features there with the super Earths, but we may get a whole bunch of things that are intermediate between rocks and ice and water-rich worlds and sub-Neptunes. And so mass does not tell you everything, but at least gives you a starting point. And unfortunately, we're not going to have radius unless the planet transits. We're not going to have radius unless the planet transits, or you detect it in the IR with an interferometer, which we're not going to have in the near future, but maybe later in this century we may. But as a starting point, you like to start with the mass. There was as Aki mentioned, the LUVOIR and HABEX studies were sort of designed with, for the search for biosignatures with the evolution of the Earth in mind, and the different, phases of life that the Earth has gone through. Its atmosphere has changed. It's only become oxygen rich the last couple gigayears. And so, at least for the one habitable world we know, it's been a bit of a moving target in terms of what its spectra has looked like over the years. But, we want to look for water and oxygen and such. And for when the atmosphere had very little oxygen, we can at least go look for ozone in the ultraviolet. And again, with a mass, when we actually take a spectrum and want to analyze the spectrum, model the atmosphere, and then put it in evolutionary context, we're going to want to know the mass of the planet for building models of the planet and its atmosphere. And we also want to know how old the system is and place it in an evolutionary context. So the Exoplanet Science Strategy was published in 2018, and it had some recommendations about mass. First off, it said NASA should go in the direction of building a large direct imaging mission to detect reflected light spectra of terrestrial rocky planets. On the mass side, it said, look, we really should keep improving the extreme precision radial velocity method. And by the way, it's hard. We've reached, below the meter per second level. We're really struggling with detecting planets and finding repeatable signals. And that technique needs to get pushed further, okay? So you start running into issues with the stellar variability at about the 1 meter per second level. We really need to get down to about the 10 centimeter per second level to detect Earths around sun-like stars. So the ESS recommended that NASA and NSF establish a strategic initiative and extremely precise radial velocities to measure masses. This had a lot of traction when the ESS came out. We had a working group put together I'll talk a little bit about that report later, talk a little about EPRV in a little bit more detail. But at least got us thinking about what the radial velocity, what the path could look like for EPRV to help provide the solution for providing masses and orbits for these directly imaged planets, should the Decadal actually select a direct imaging mission, which it ended up doing. Now, after that radial velocity recommendation, there was no recommendation on astrometry. There was a finding on astrometry, which was, it basically came out like, if EPRV doesn't work, break glass, do astrometry. That's that. It was basically a paragraph in the ESS. It was a little bit underwhelming. But we need to, we need to start thinking again about astrometry strategically now in light of this decadal recommendation for the 6 meter. And I'll talk about that a little bit here in the last couple slides. But this is just a finding in the ESS, and there really wasn't much mention of astrometry in the actual decadal, but some mix of EPRV and astrometry is going to have to fill the gap for detecting, for measuring the masses and orbits for the planets that the decadal ERUV mission will detect. This is my one equation in the talk. For the radial velocity amplitudes, for an Earth-like planet around a solar twin, where it works out to about 9 centimeters per second, and you've got sensitivity in there by mass and semi-major axis and eccentricity. For astrometry, it works out that an Earth twin, one Earth mass planet, one solar mass star, 1 parsec is 3 microarc seconds. We happen to have a couple solar type stars at 1 parsec, Alpha Centauri and B, and those amplitudes are roughly 3 microarc seconds. Unfortunately, the situation is not that. Even 3 microarc seconds sounds really hard. The situation is not as good for the other stars within 10 or 20 parsecs, and I'll show you a plot. So back to EPRV. So again, if you look at the measurements of EPRV over time, let's see, does my finger come up on here? If you look over the EPRV detected planets, the amplitudes decreased over time to about 2010, and they sort of flattened out through the 2010s. We sort of hit this meter per second barrier. Nowadays, there's more and more detections below meter per second, and I plot a couple here for the Tau Ceti G and F components. I'm not sure how strongly people in the community feel about the reality of those, but I think they're there as confirmed planets in the exoplanet archive at this point. But they're really pushing the EPRV limits for Tau Ceti. So this is a magnitude 3.8, very, very quiet solar type star with 1,000 observations. They're pushing the technique down to measuring tens of centimeter per second amplitudes. Now for an Earth twin, it's 9 centimeters per second. For a 1 solar mass star. As you go down through the Ks and Ms, it becomes easier. And to a certain extent, we're kind of in the era right now of detecting Earth-like planets in the habitable zones of M dwarfs. If you've seen all the results from spectrographs like Carmenez and HPF and others, HARPS, we're detecting planets now around M dwarfs. Proxima Centauri B, perfect example, 1.3 Earth mass planet, 15-day orbit around a 0.12 solar mass star. That's now doable now. But as soon as that's for very low mass stars, as soon as you get up to 1 solar mass and the habitable zone moves out, the temperate planets are moving out, and the stars are becoming heavier, and the radial velocity signal is becoming smaller. The EPRV has some struggles at different points here. What are you up against? One is photons. One is just you need stars to be particularly bright. The spectrum itself has information content. You're looking for nice, clean spectral features. And some of the stars are very active, or they're very fast rotating, and they blur out those features, and it's more difficult to centroid on. The full width half max, if you put it in those terms, becomes wider. There's instrumental effects. How stable is the instrument? No detector is perfect. Your calibration source, your calibration light source, the calibration may wander around a little bit. How stable is your pipeline? And then there's the star, and the star has all sorts of gremlins. There's all sorts of things going on with the star. The star has spots. The star is active. The star is convecting. There's cool and hot and cool areas. The stars flare. There's very subtle changes with flows in the stellar photosphere. There's a lot of things that can contribute to very small variations in the radial velocity at the sub-meter per second level. And even for the sun, it's worth noting, I don't think yet, even given the observations of the sun, that the Earth or Venus at the sort of 8 or 9 centimeter per second level has been detected from solar EPRV observations yet. That is that'll be a real breakthrough when that's done for the sun. So there's all these different components, all these different parts of why EPRV is hard at this level, but it's making headway. The thing is, EPRV has been making very steady progress. It's the gift that keeps on giving. You can go back and analyze these archival data sets and apply some new techniques, and you'll pull new planets out. And so we're sort of slowly moving down to the Earth regime around the sun-like stars with EPRV. So after the ESS came out, we had this EPRV working group final report that came together that was just looking at what the future could look like. And basically, from the NASA side, the question is, can EPRV get to the 10 centimeter per second level and inform architectures? Uh-oh, am I running out of time already? Oh, shoot. Okay, I had less than I thought. Okay, well, I'm going to move ahead. Sorry, I wasn't even looking at that. The LUVOIR report had a little bit on astrometry as an option. This certainly needs to be developed a lot more. I think, and as Zaki said, there's a lot more work to be done exploring those. This is a plot of radial velocity amplitudes versus astrometry. And where we need to get down to, this is in log 10, okay? We're trying to get down to meter per second level down to the 10 centimeter per second level. With astrometry, we're trying to get down to the milliarc second level to the sub-microarc second level. And really, there's actually a bigger gap with astrometry. We're just starting to get the first detections now in the sort of 100 to 300 microarc second regime, but there's still a big way to go. Those targets for the ERUV, this is plotting targets for the LUVOIR and HABEX, but they're basically naked eye FGK stars. They're down at the sort of 10 centimeter per second and 0.3 microarc second regime. The precursor knowledge is important. If we can we know where to point the ERUV initially, you can get the yields faster. Okay, imagine we know where the planets are and we can launch the spacecraft and point and go zap, 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 zap. We'll be able to do initial coronagraph survey, this is with HABEX with the star shade, so it's a little bit more pronounced because the star shades takes more to move it around. So I'll just say, look, there's open questions here we need to solve here soon. What degree of precursor knowledge do we want for the masses and orbits of the exoplanets that ERUV is going to image? What are the astrophysical and technical limits to the accuracy of astrometry and radial velocity techniques with respect to the goals of measuring accurate masses for those potentially habitable worlds? What are the astrometry capability options? We need to develop the options here, and we've heard about some of them today in support of the ERUV exoplanet imaging. And really, we need a strategy, right? We have an EPRV working group sort of gave us a strategy of what EPRV could do in the future. I think we're going to need the community to come together and come up with an astrometry strategy. Explore the options, how do we go forward and support this quest to find habitable worlds around the nearby stars with ERUV. So unfortunately, I'm just going to close there. I'm already a few minutes over. So there's a few things to explore here with what do we do? Do we do nothing? Do we explore EPRV and astrometry as precursor science so that we've got a target list ahead of time at the beginning of the mission? Or do we just develop the options and say, we're just going to get the masses afterwards? I think it'd be much more compelling. We've just gone through this with James Webb Space Telescope with the initial images. Wouldn't it be great to show within first few months of the ERUV spectra of potentially habitable worlds? Because we knew where to point. And we already had the information to start telling the story about what those spectra mean. So I'll leave it there. Thank you. Apologies for not paying close attention to the clock.
I'm afraid Eric burned his question time. So if you have any questions for him, please take him to the break.